Uh, a very good afternoon to all the student friends. This is Yashwant Kolekar, and I was introduced by my friend Vivek himself. Before I begin with the today's presentation, I would like to share two or three things. First, initially, I would like to thank the Ramdev Baba College of Engineering, Nagpur, because in this particular times or durations which the entire globe is passing through, they are taking and ensuring that the knowledge dissemination to the students and participation of the academicians and research scholars doesn't remain behind. So because they are taking up for the last 2 to 3 weeks, webinar series is being conducted by them. So I thank the entire Department of Civil Engineering, Vivek. Another thing before proceeding with the today's presentation for stone columns. So actually this presentation has to be covered in 3 days. So because of that, the shortcoming, what we are going to do presently, we are going to cover ground improvement and ground improvement using stone columns. The second part, which consists is regarding the design part. Design part will be very, very briefly covered in this particular presentation because it will be requiring a different presentation altogether. And third part for the stone columns is the latest state of art research going in different laboratories and institutes across the globe. So the entire stone column, which is used for ground improvement, can be classified in these three types of presentations. So today we'll go with the first type of presentation, that is ground improvement, and then stone column, and in brief design and site visit that we had carried out at Pipavav, Gujarat. So that will be shared. So I thank one and all in the initially itself for registering for this particular webinar. So I will begin with my presentation. So my email address and the cell number is the host institute to share with the participants later on also. In the beginning, I pay my regards to my parents. My father was a geologist himself at ONGC Mehsana, and my teachers, particularly Professor Maheskar, who is presently Vice Chancellor at PSTME, Mumbai, Mukesh Patel School of Technology and Management and Engineering, and my other teacher, Professor Satyanarayana, who is professor at IIT Bombay. So it's because of them today I am there in geotechnical engineering. So before we begin with the presentation, the Chhatrapati Shivaji Maharaj, as everybody knows, he was a king, and all the Indians across the globe also, we love him. We know him as a king, we know him as a kind-hearted, and most of us also consider him as a god. We also know that he had more than 300 forts under him. We're just going to pass a brief 5 to 10 minutes, not more than that. He had more than 300 forts built. Many of them were constructed by him, and remaining were either maintained, modified, or reconstructed as per his requirement. Here I would like to highlight that he was not only a king or not only a people's person. Apart from that, he was an engineer also. Because a person having nearly 300 forts under him has to have some more than minimum information regarding the engineering that was existing during these periods of 16th century. So we all pay our regards to him. Still into the history, Indian history and the some global history, I'll be sharing some photographs of old structures that are existing still today with pride. Now, how these are related to ground improvement, we'll see it later on. So these are the 4 forts which were under Chhatrapati Shivaji Maharaj, the Shivneri Fort where he was born, the Purandar Fort where another Chhatrapati, the second Chhatrapati of Maratha dynasty, that is Shambhaji Maharaj was born. Then we have got Raigad, which was the capital of Chhatrapati Shivaji Maharaj, the Pratapgarh Fort near Mahabaleshwar and Satara. Then we have this beautiful Janjira Fort. As everybody knows, it is located in ocean. And from the aerial photograph that is shown there, it can be clear that it has got water of significant depth on all its sides. Then we have got Sinhagad Fort, the valor of Tanaji Malusare is known to everybody. Then Naldurg Fort in the Usmanabad district. There nearby we have got columnar
Yashwant sir,
geological
sorry to interrupt
formation,
you.
and it has got. हाँ बोल.
तो वॉइस कट होतोय तो थोडा माइक जवळ धरला तर बरोबर मला वाटतं. त्याच्यामुळे वॉइस
माइक
कट होतो.
घेतलेला नाही मी.
अच्छा ओके.
Hello.
आता
audible now?
yes yes. Now it is correct.
So we had just begun with the ground improvement, and before going to improvement, why improvement is required? So we are just going into the history of the world and particularly of India, and a brief information about Shivaji Maharaj, whom we feel he was not only a king, etc., but apart from that he was an engineer also. So the forts under him. Now here we have got few other structures that are still existing. The Golden Temple, Darbar Sahib is fondly known. It was constructed in 1590 CE by Guru Arjan. Then we have got the Hawa Mahal, the old and the new Somnath temples, both are existing there. And the previous one, which was plundered by the Ghazni, etc., that was constructed, completed in 649 CE. Then we have got this fantastic Jantar Mantar, which takes care of the science and astrosciences also. Then 1602 CE, we have Buland Darwaza that was constructed by Akbar himself. Then we have Makkah Masjid that was constructed by the Hyderabad ruler in 1614. And the magnificent Qutub Minar still standing tall in the vicinity of New Delhi. That was constructed in different stages, started in 1200 and was completed in 1368. Now here you have this particular Tawang monastery in Arunachal Pradesh. It was constructed in 1680. Then 7th century BC, we have got Nalanda still standing there with pride. The temple at Hampi and the some famous Sun Konark temple of 1255. Few more magnificent structures. The oldest existing temple in India, 180 AD, or of Ma Mundeshwari. And the old man-made structure is in France, that is Barnes, and the famous Giza, and our own Samrat Ashok, who had constructed the Sachi Stupa, still it is there, and the magnificent Taj Mahal. Now these are some of the structures, and still many more are there. All these structures are still standing there. Now before we go into ground improvement, now apart from any natural disaster like an earthquake or lightning, etc., nothing else has affected all these magnificent monuments and structures that are existing on the globe. And many more are there. So the engineering that was there during those times, so they were selecting the site in such a way that
still there has not been any foundation problem. The masterpiece Taj Mahal presently that we are seeing or having a look at it, it's everybody knows it is situated on the banks of river Yamuna. It must have been flooded many times, that particular region and area and tract. But still, the foundation remains intact, and we all know that sunk foundation has been taken up, sunk cylindrical foundations have been taken there, and it's entirely of entire stretch consists of sand beds. Now, when we look at this, all these magnificent structures which are still standing, so we come to know that the ground below them, on which they all are standing, is firm, sound, and stable. Now, with gradual entry into the 19th century, when there was a population explosion, and as everybody knows, that before 19th century, most of the constructions were done by army people. So the term civil engineering came into existence in the latter phase of 19th century, because different people were required to provide the necessary shelter facilities for the civilians, and then the term came into as civil engineering. Now, an improvement is required when there is some weakness. Strengthening is required when the qualities of not suitable material, when it is poor. So this we all know, we understand. Strengthening or improvement is required for any material or anything on the globe if it is not having that required capacity to withstand the given load or the design load. Now, what happened with the population explosion in the first quarter of 19th century across the globe, and particularly in the Asian continent? Most of the good sites or sites with good quality soils were utilized. Another thing, because of scarcity of good sites, people or the engineers started shifting to poor sites, or the sites where the strength or bearing capacity of the soil was insufficient. Now, if the strength of the soil is less or its capacity is less, that means we have to provide an additional boost of strength so that it can stand the design load. So, with that brief into the history of the good foundation structures still standing all with pride on good foundations. Now, we have other sites or location where the soil is not good. Here I would like to quote an example from the past history, which everybody knows is the Leaning Tower of Pisa, because it had some problem, some issues with the soft soil that was located in the foundation. It tilted, and now that particular tilt has been controlled with various measures that have been adopted. So we go into the introduction to ground improvement. As I said, for suitable sites, we don't have any problem. We can go on constructing. But for unsuitable site conditions or for poor soil site conditions, if they are encountered or we come across as an engineer, so we have to tackle them. We cannot say or run away from the problem that since the soil conditions are not proper, the structure cannot be constructed. No, we have to provide a solution as a geotechnical engineer. So in that case, Professor Mitchell in 1976 has suggested various measures so that if they are adopted, the soils with poor capacities or strength can be enhanced. So what do you mean? The first parameter that he has said is that bypass the unsuitable soil by means of deep foundations. That means you take your foundations, bypass the soft soil strata, and rest your foundations on the firm strata. Now, if this condition is valid only if your firm strata is available at a shallow depth, maybe 5 meters, 10 meters. Suppose if your firm strata is available at a depth of 50 meters Are you going to take your foundation to that particular depth? It will become highly uneconomical. The project will run into cost overruns. Second one is redesign the structure. We'll have to redesign the structure and its foundations so that whatever the existing strength of that particular soil is there, it can withstand the superimposed load after this structure comes into existence. So again, that means redesigning means recalculation and everything will come into picture. Third method that he had suggested was removing the poor material and either treat it to improve and replace it. So you have an option that you can remove the entire poor material or a part of it and treat it and again replace it by suitable material. Mentioned is that treat the soil in situ as it is. Don't disturb the in situ soil. Don't disturb the navy soil or the virgin soil and treat it there itself to improve the properties so that the required strength is accomplished. So again, according to him, ground movement in the broadest sense is nothing but the alteration. Here we are going to modify the properties of the natural soil or rock at the site itself to improve its engineering performance. And this particular improvement or the measure that we are going to provide temporary or permanent measure depending upon the requirement. So what are the different factors that govern the ground improvement? First is the soil type or the rock type at that particular site. Then the area and depth of treatment that is required. If our firm strata, as we had just seen, if it is located at 50 meters or 30 meters below or even 20 meters below, so are we going to replace the entire soil? No. So what is the area of the site that is to be treated and up to what depth the treatment is required to be provided to the soil? The type of structure that is going to come, if they are silos or if we have got warehouses, etc. And apart from that, the load distribution that is going to take place because of that particular structure on the soil. So with a wider base, naturally the pressure that will be coming on the soil will be less, and the load distribution, if it is uniformly distributed, that will be a better one. And the soil properties, as we all know, will be playing the major role. So these are the factors referred by Michel in 1976 that are going to impact the ground improvement to be adopted. Later on, again in his in 1981, Dr. Michel has given the different methods or techniques that can be adopted depending upon the grain size, particle size of the soil that is there at the site. To the top in the graph, you can see the gravel is on the left, whereas in the clay on the right, and the various methods that are there that were existing in 1981. So he has listed them out for gravel to sand soils if they are there. So the list is vibro, compaction, blasting, particulate grout, and chemical grout, etc. And as we come to clay, the admixtures, thermal treatment, reinforcement, particularly will there. For us, we have electroosmosis and dynamic consolidation, dynamic tamping, etc. will be also there, compaction. So these are the different methods that will be adopted or that are suitable for the different particle sizes. Schoffer in 1997 in his paper had listed out or classified the ground improvement techniques into ground reinforcement, ground improvement, and ground treatment, basic three major classifications. So the list is long. We'll see few of them in brief and stone column in detail. So reinforcement, we can see stone columns, soil nails, micropies, etc. For ground improvement, we have deep damping, compaction, drainage surcharge or vacuum preloading. We have got electroosmosis, grouting plus, etc. and PVDs also, and treatment with the different mechanical, these chemical admixtures that are there, and heating and freezing to be is also provided there. So these are the different ground improvement techniques in three major classifications. Further, this particular flow chart was given by Terashi and Tanaka in 1998 in their paper. So this is a general guideline as to how you should follow and what method is to be adopted and what quality checks and quality assurances and to be adopted during the construction and even after post construction for monitoring. And the various factors that affect them are the site conditions and topography, obviously. Michel and Menten mentioned regarding the soil properties. So what are the few properties I listed out? As we all know, that ground improvement mostly is done for the fine grained soils with few applications even to the coarser fraction. So cohesion plays an important role for fine grained soils. Then the angle phi, the permeability, the void ratio E, the past stress history of that particular soil, the capacity or the strength, the deformation characteristics, stress strain behavior, the creep, etc. Since economics is related to the importance and nature of the project, so this will also be taken into account. Then the depth up to which the treatment is required, and finally the project economics. So these are the various factors that are going to govern the methods that we are going to have, and the flow chart has been shown that. The flow chart indicates, if you go through them, some of the tests on the soil will be carried out in the laboratory and some in the site. After we get those parameters, the design for the ground improvement technique and the cost comparison is taken out. Then the problem is associated at the site. At different sites, the problems that will be facing will be different. So each site will be a unique site, and the site specific problem solutions we will have to suggest. And finally, the completion of work and monitoring for maintenance. So this has to be carried out for years, depending upon the type of project and its importance. For some of the projects, it may be 4 to 5 years, and some few projects it may go beyond 20 years. Again, from this particular graph that was given by Nuzu in 2000, as I had said in the initial phase itself, initially good sites were available in a big amount, in a big number. So during those days, since we had a good foundation, firm strata, so the stability was the only criteria. But with the lesser availability of good sites and more number of poor sites available for constructions and the different projects, so these different parameters came into existence, like the settlement criteria. Then we had shear, then the deformation, earthquake resistance, the environmental impact studies were required to be carried out in the recent 2 to 3 decades back. It has started, and the environmental conservation and sustainability. So these are the different engineering issues that will be governing the performance and the site selections also. So the various factors affecting the selection, as we have seen, the list of the ground improvement techniques that are available is long. So which is the best one? As an engineer, you will be required to suggest to your client or to your firm. It's your responsibility. So what are the factors that are going to govern this method or technique that you are going to suggest for that particular site? So About 8 to 10 parameters have been listed out here. The degree of improvement, type and degree, the type of soil, then the equipment specification in the tenders and the cost that will be involved for the project, the time that is available for the construction, whether any structures are there or pollution to the groundwater resources and possible damage to both of them, the materials that are going to be used, because lately we have been using geosynthetic materials, etc. Durability of the materials that will be used as an reinforcing material, so that is also going to govern there. So durability of this material will be playing a vital role. Then the toxicity, if any chemical admixtures are going to be used, so whether they are toxic in nature and they are going to have any impact on the soil behavior as well as the pore water. Then the chemicals, the reversibility and irreversibility of the processes, the reliability methods, feasibility of construction controls, and the performance measurements. So the same, all these parameters again in brief. Type and degree of improvement that will be required is the bearing capacity, the reduction in settlement, obviously. Then the long-term and short-term performance and the resistance to liquefaction for the sites that are located in the seismic prone areas. That is if we consider the this India, then Gujarat, then the Himalayan belt, and recently even the southern part of Maharashtra has come into this particular zone, seismic zone. Sorry. Then the type of soil, the geological structure that is there, and the seepage conditions that are existing within the soil, they are going to play a role. So the pore pressure and the seepage and the presence of any difficult soil conditions. Then the improvement technique that will be adopted will depend upon the equipments that will be required. And lately we all know sophisticated and very extremely costly equipments are being put to use for ground improvement and as well as in infrastructure projects. The construction time is always a constraint for the engineers, and so if any accelerated construction techniques are there and if we are going to use them, so what measures will be required to be adopted? Then the damage to the adjacent structure and the pollution, so we'll be required to monitor them. And regarding the pollution, contamination, etc., and monitor regarding the adjacent structures, because damage to an adjacent structure will not be an instant one. It will show you some signs, and you should be able to pick up those signs given by the adjacent structures regarding the transfer of any energy to the adjacent foundation. Because if you are going for any compaction, etc., or dynamic compaction, so the wave or the energy travels through the soil media to the adjacent foundation and is likely to create vibrations in the foundation, which is then transferred to the superstructure. We have the default regarding this geosynthetic material particularly. Then the corrosivity, in case mixtures are used, the reversibility and irreversibility of processes, the reliability of the methods, and feasibility of construction controls, etc. Now, why ground improvement is required? What is the aim and objective? So, these objectives have been provided by Barksdale. Somehow that particular reference tag is missing here. So these are suggested by Barksdale and Backus in their report. They had submitted to FHWA USA, and I would like to make a special mention. This particular report that was submitted by Barksdale and Backus is considered as an Bible or Gita or Quran for stone columns. So it became, for a person working in stone columns, he has to refer to this particular report, and it's available there. So the objectives or the aims: enhancing the bearing capacity, minimize the distortion under the stresses, reducing the compressibility of the soft soil. Obviously, it's a poor or soft soil. That means it will be having a higher void ratio, so it can be easily compressible, and settlements can be reduced or minimized. So we have to reduce the compressibility so that the settlements are minimized. Then we have to take care that there are no physical or chemical effects on the soil and the soil structure, particularly in case of extreme weather conditions. The sites which are located for the sites located in areas, and I would like to mention here that stone columns have proved themselves that they can withstand seismic activity comfortably. Then we have for reducing the natural variability of the borrow materials in the foundation soils that will be required. Some of the techniques apart from stone columns, we'll just go in brief. Soil nailing, as we all know. So these are provided for stabilizing a slope, which will be an man-made or natural drilling holes and thereby inserting the steel bars and then plugging them with proper grout. The next one is your micropiles. The list was given by Schoffer and as well as Michel regarding the different techniques or methods that are available for ground improvement. So micropiles is also there. So these are nothing but the small diameter drilled and grouted friction piles. Here a steel element is bonded into the bearing with a proper cement grout, and this grout has to be designed properly. Then the jet grouting. Here under high pressure, the grouts are injected into the soil below, thereby breaking the soil structure and simultaneously the mix cement grout with the parent soil there. Provided these are supporting the structures in geotechnical as well as construction applications. So they can be either driven or maybe spirally driven, and are used in both temporary or permanent applications for retaining walls, masts, as well as for tents. Geosynthetics is being used in a big way. They are nothing but the polymers, and depending upon the applications, they will be suggested. They are provided for strength improvement. They are also provided for preventing or minimizing the permeability. They are also provided for enhancing the permeability depending upon the site requirement or the soil that is available at the site. Then the lime columns. For deep soil mixing, this particular method is used in case of soft, clay or poor soil deposits. Then the vibro concrete column has been shown that mixers are there pumping the concrete into the bore or the hole that has been dug, and simultaneously the compaction is carried out so that we get a good dense concrete column. In case of deep dynamic compaction, tampers of weights ranging from 3 to 5 to 30 tons and with a drop of 10 to 30 meters is provided, and overlap has to be proper overlap has to be taken care accordingly. The design of the spacing design regarding the spacing of the locations where the tamper should fall has to be provided. So here we can see in the right hand side figure the overlap because of the impact energy to the soil below. So this overlap has to be proper so that the effect will be maximum. Then we have got another method, that is either drainage for surcharge or for preloading, that is adopted for ground improvement. So here during the construction process, construction duration itself, the consolidation of the soil takes place by removal of the excess pore water pressure, thereby increasing the strength of the soil. Electrostatics method is adopted, wherein the current is passed through the soil and the current flows from anode to cathode, that is from positive to negative. And during this particular flow, the flow of pore water starts and the water is removed. Pore water is removed from the soil, thereby increasing the strength. PVDs basically are used for draining of the pore water pressure. They don't add anything to the strength of the soil. They just act as a drainage path for removing the pore water. Now, our area that we are going to focus today is the stone columns. Just now we had seen some of the techniques that are there. In brief, we had seen few of them. Now we'll see stone columns in a detail. What are stone columns? As we all know, that for soft soils or very soft soils, the structure cannot stand on it. As soon as it is subjected to any type of loading, it starts sinking, it starts settling. Now here what is done? With the help of a probe, holes are drilled, the soil is taken out, and this hole is again filled with a more stronger material with a greater strength, that is aggregates and nothing else. No other admixture is added in case of stone columns, only aggregates of different sizes depending upon the method that we are going to adopt, whether it is a wet method or a dry method. So stone columns, what are they? They are defined as by Barksdale and Backus in the report of 1983. They are the densified forced intrusions in the form of vertical columns of aggregates of a specific diameter and depth that has to be designed, and it is provided in soft soils. And why these are provided? So as to improve the inherent properties. And by providing these stone columns, the bearing capacity increases, the slope stability of the embankments as well as the natural slope improves. It helps in reducing the total as well as the differential settlements of the structure. It significantly dissipates and removes the excess pore water pressure, pore water, and minimizes the liquefaction potential. So these are the benefits or advantage of providing a stone column in soft soils. Further, in case of stone columns, will be suitable if we move 15 to 13% of the weak soil. Now, this is the range of a particular site of which the total volume of soil that is available, 15 to 35% of the weak soil has to be only replaced by the aggregates. So if we replace soils less than 15%, what is going to happen is that proper strength will not be achieved, however strong your aggregates may be. And if you remove a weak soil greater than 35% and replace them by aggregates, the project goes into cost overruns and the economics is disturbed. So we should see that at a particular site, the removal of the weak soil in terms of volume should be in the range of 15 to 35%. Once these stone columns are constructed, their design loads range from 20 to 50 tons per stone column. And these stone columns support structures where the soil is either very soft soil, firm cohesive soils, or sands, loose silty sands where the fines are greater than 15%. Now these stone columns are suitable for shear strength of the soil at the site if it is in the range of 15 to 50 kilonewton per meter square or kilopascals. But there have been some cases, exceptional cases, where the strength of the shear strength of the soil is as low as 7 kPa or 7 kilonewton per meter square, and still stone columns have been successfully installed. So their specific measures were adopted, but in general, if the soil strength, shear strength is in the range of 15 to 50 kilonewtons per meter square, your providing the stone columns will be very economical and optimum. For if the shear strength of the soil is greater than 50 kilonewton per meter square, or in the range of 50 to 100 kilonewton per meter square, so in that case, if you are going to provide stone columns, then the contractors who are providing will be facing a stiff resistance from the soil. So that will be affecting not only the equipment that are being used at the site, but at the same time, the time duration will also increase and the cost economics will increase. So the 7 kilonewton per lower allowable limit, in exceptional cases it has been adopted, and for upper limit is 50 to 100 kPa, not beyond. So stone columns are suitable where the soil properties or the soil strength is between 15 to 50 kPa. What are the potential applications for the stone column? So these are the few applications. As an embankment for fill support for highways, interchanges, bridge approaches, railways, etc. For highway facilities, then structures, then concrete library, etc. has been constructed for LNG, which are mostly located across the coastal lines. Now here, how is a stone column? Actually, we thought of showing a video, but there was a possibility of some disruption during the presentation. So we thought of having this animated process, entire process of animation of stone column installed at the site. Was done by myself when I was doing my research work under Professor Murthy at IIT Bombay. So for this particular animation, then we had submitted to IIT Bombay also. So this is how the animation works. So we are assuming that we have got different stratas, strata 1, 2, and 3, and the assembly has been shown there. The probe is there, and the water is coming out the tip of the probe. So assembly moves. So we'll start with the animation. So we are going down to the desired depth or the design depth that has been up to depth up to which the improvement is required gradually. So the hole is constructed to the design depth, and the form strata which is located at up till that particular depth we have a hole. Then this hole is flushed 2 to 3 times, and then what we do, there are two different methods that are adopted for stone columns. One is wet method and dry method. We'll see it later on. So here what we are doing is, now once the hole is big and then it is flushed to remove the silt, etc. Now we start placing the aggregates, and simultaneously compaction is carried out. Now gradually we move up to the ground level and the stone column is complete. Once the stone column is complete, the design regarding the spacing that is provided and the entire probe moves to the next specified location where the stone column is to be provided or installed, and then again the process is repeated. So this is how the animation works, and this is how the stone column is installation at the site is done. Now the probe that we have seen in the animation and the method that we have been referring consistently, that is a wet method and dry method. So these are the probes, and these probes have been, the figures of these particular probes have been taken from Keller, India. Now the left hand side, if you see, we have got a probe that is suitable for wet method to be adopted, and the right probe that is there for the dry method. Now, in both the probes, you can see an eccentric weight that has been provided. Inbuilt eccentric weight is provided so that during the vibration, because of the eccentric weight, what happens? Your probe moves laterally, and this helps in having a bigger diameter hole. These probes, they are generally available in the diameter of 500 mm, 400 mm, 700 mm, and up to 1.2 meter. Now, because of this eccentric weight, what happens? We can have a bigger diameter. Because of this eccentric weight, the lateral vibrations are imparted to the surrounding soil, and a bigger diameter hole is provided. So in case of wet method, obviously we are going to make use of a water jet under pressure to drill the hole. Whereas in case of dry method, compressed air basically made use of in case of dry method. So at the tip, you can see the aggregates are coming out in case of a dry method. And in case of wet method, from this particular tip, the water jet comes out under pressure. Now this probe also is used for compacting or densifying once we move up. So gradually we move up layers, we compact it. Again, the second layer of aggregates is allowed to fall into the hole. That again, second consignment of aggregates is compacted or densified using the probe. Again, the third consignment of the aggregate comes and gradually move up. So depending upon the soil conditions, the wet method or the dry method is adopted, where the partially saturated, in case of soil is partially saturated, the dry method is adopted, and whereas the soil is highly saturated, in those conditions, wet method will be adopted. But most of the contractors, they prefer wet method. So this is the comparison for the classification for both the methods. In case of wet, bigger size of aggregates are used as compared to the vibro displacement. In case of wet method, we can see the diameter that is accomplished or achieved is bigger as compared to the vibro displacement. Dry method, in case of dry method, the diameter of the stone column is smaller as compared to the diameter that is achieved in case of a wet method.
Sir, sorry to
In case
interrupt.
of,
Sorry to interrupt. The voice is breaking. Voice का थोड़ा issue आ रहा है.
अभी clear है?
अभी clear है, correct.
Hello. Hello.
अभी clear है.
Okay. Okay. In case of wet method, the soil is removed at the top, because the water that is used for water jet that is used for creating the hole, the same water comes out onto at the ground level, and while coming up, it brings the soil that has been loosened because of this particular probe. So in case of wet method, the soil comes to the top, whereas in case of dry method, the soil remains within the hole itself, and it is pushed laterally downwards. Now we had visited this particular Pipava project. The stone column constructions were going on. So there we can see the wet method as well as dry method. In case of wet method, we can see a pool of water aggregates. Lifted and then again inserted, gradually is lifted and again inserted. Internet connection is unstable. So So when this probe is pulled out, the aggregate when we reach the design depth or the desired depth for making after making the hole to the desired depth is we are reached with the help of a probe. Then these aggregates are dumped near the hole with the probe still there inside. With the probe still there inside, with the help of a truck, these aggregates are dumped there, and the probe is slightly lifted. So these aggregates fall down. Then again the probe compacts them, and again it is lifted. Again, this second consignment of the aggregates falls down into the hole. Whereas in case of dry method, there we can see. So this is an hooper that is provided. So aggregates are it's filled with the aggregates, and this entire assembly goes up. Now here we can see there is an opening that is provided. Now this hooper is lifted to this particular location, and through this opening that is provided in this particular probe, the aggregate here a gate is provided. As soon as this hooper reaches this particular window or opening that is provided in the probe, the gate is opened, and the entire consignment of the aggregates that are there, that is there in the hooper, falls into the through this window opening or door to the probe and to the hole below. How does this particular stone column work? Because we have rigid pile or the concrete pile on the left hand side in the figure, as well as a stone column. The basic difference between a concrete pile and a stone column is that cement is missing. The binding agent or the binding material is missing in case of a stone column. In case of rigid pile, even if it is cast in situ or precast, concrete acts as an binding agent. So it binds all the aggregates which are inert as well as the sand together in case of a concrete pile. But whereas in case of stone columns, only granular material aggregates, stone aggregates are provided. So there is no bonding between the aggregates as they are inert material. So when this particular stone columns is subjected to loading, it undergoes a bulging, and it has been observed at site as well as in the laboratory tests that this bulging is located at a depth of 2 to 3 times diameter of the stone column. Stone column, it's provided where the compressibility is lower. It helps us in achieving higher shear strength. There will be concentration of stresses because the surrounding soil is very weak, whereas the stiffness of stone column as compared to the stiffness of the surrounding clay or soft soil is very low. So there will be concentration of stresses on the stone column, and due to this, the bulging takes place, and additional confinement is provided by the surrounding pressure that is subjected by the soft soil. Now, for understanding the behavior and for carrying out the studies, the unit cell concept was suggested by Barksdale and Backus. So here we can see in the figure 7 stone columns have been shown in plan, and a centrally located stone column is there. Now this unit cell is nothing but an imaginary cylinder, and when this particular central stone column is loaded, the influence zone of the pressure gets transmitted laterally also. So what is the influence zone? Up to what lateral distance the pressure gets transmitted? So that defines the diameter of this particular unit cell. So unit cell is nothing but an imaginary cylinder of equivalent diameter, up to which the influence of a stone column is assumed to exist to the full limiting axial stress. So this is the influence zone is going to help us in deciding the spacing of the stone columns, because beyond the influence zone we will have to provide another stone column, so that the no soil, no region of soil, no zone of soil remains without any pressure because of the stone columns. So the spacing that has been suggested Either we can have a square grid pattern or a equilateral triangular pattern, and S stands for the spacing between the stone columns, D is the effective diameter, and the ratio multiplying factor is 1.13 for square grid, as well as whereas for equilateral it is 1.05. There is another term here we come across is the area replacement ratio. Area replacement ratio, if you go back to the unit cell concept itself, the stone column has got certain volume, and the unit cell is a imaginary cylinder has got certain volume. The volume of soil that will be replaced for installing a stone column will give us this particular parameter, area replacement ratio. Because if we are going to provide bigger replacement of soil by a greater amount of aggregates, obviously the strength will increase. And if your area replacement ratio where the replacement of the soil is on a lower side, so the strength of the stone columns will not be achieved as per the design suggested. So area replacement ratio has to be taken into account, and it is an important factor controlling the design as well as functioning of the stone columns. Now, once the stone columns are entire site is covered with the spacing of number of stone columns, and the site stone column installation, the site is over, then a granular blanket of clean sand, which is medium to coarse, has to be provided with compaction, and this minimum thickness of the sand blanket has to be 0.5 meters. And this helps because what happens in case of stone columns, when it is subjected to loading, the pore water pressure finds its way laterally into the stone columns. When the stone columns are subjected to any loading, if because of this particular loading, what happens, the squeezing of the soil starts taking place, a deformation starts also because of which bulging is also introduced, and because of this the pressure that is transferred to the surrounding soil, the pressure in the pore water starts building up, and this water enters circumferentially into this particular stone column and then finally finds its way to the ground level. Since we are making use of the aggregates and no binding material, there are voids in this particular stone column, and these voids provide the pathway for the pore water to come to the ground level. So when this water reaches the ground level, it has to be absorbed by this blanket and so that is one of the objectives or aim of providing granular blanket, and it is ensured because not in the case of dry method, but in case of wet method, we see there a pool of water as well as lot of silt and clay coming to the ground level along with the water. So obviously a slush is formed. The entire site area becomes slushy. So this slush has to be first removed, and then the sand layer has to be provided, or the granular blanket has to be provided. Then what are the various factors that are affecting the capacity of a stone column? As we had seen in the figure that was given by Hughes and Wither, this figure has been taken from Hughes and Wither's 1974. The resistance offered by the surrounding soil to the lateral deformation because of the bulging phenomena that is taking place, and this bulge, I again repeat, takes place at a depth of 2 to 3 times the diameter of the stone column. Then the resistance that is offered by the surrounding soil due to the surcharge that is placed in the form of a sand blanket or minimum sand blanket that is provided is 75 centimeters. And when we are providing a series of stone columns, we have designed the spacing whether it is a square grid or triangular grid. So intervening soil between the stone columns that is there, it also adds to the strength. So the bearing support that is provided by this particular intervening soil, the resistance provided by the surcharge, and the resistance offered by the surrounding soil to the lateral deformation. So these are the three parameters based on which the capacity of a stone column is arrived at. So once the stone columns at a site are completed, so we are required to test whether the designed the stone columns that have been installed or constructed have attained or arrived at the designed value or the expected value. So for that particular purpose, as we conduct the plate load tests, similarly here a plate load test is carried out. If it is a single column test, the pattern has been shown here. The spacing is 1.85 meters center to center for the stone columns of diameter 900 mm. So steel plate, MS steel plate diameter has been shown and an RCC pad is formed, and then the test is carried out. For a group stone column test on a three stone columns group. So this is the pattern that is adopted. Fifteen stone columns are there, and the three stone columns they are there at the center in this equilateral triangle. So all the three stone columns at the center are loaded with a steel plate, and the strength is arrived at because of the plate load test. How do the stone columns fail? Because all the structures that are constructed in civil this geotechnical engineering, whether it is a retaining wall, a reinforced earth wall, or a pile, we carry out the studies as to understand how they fail. Somewhere in the future, some of them may fail, some of them may not fail, and if failure is there, they are likely to create chaos at the site. So as to prevent that, studies are performed at the site as well as in the laboratories to understand the failure mechanisms. The stone columns that are there are of two types. Either they can be end-bearing stone columns or floating stone columns. So end-bearing stone columns, we all know, they will be resting on a firm strata below, and floating stone columns, they will be just suspended in the soft soil itself without having any bearing on a firm strata below. Whenever the length of the stone column is greater than 3 times the diameter, bulging failure has to take place. Whether the stone column is an end bearing or whether it is a floating, when the length of the stone column is greater than 3 times the diameter, the bulging failure will take place. Whereas general shear failure or local bearing support capacity failure will take place when the length is less than 3 times the diameter of the stone column. That is for short stone columns. And end bearing failure will take place for floating stone columns where the length is less than 2 to 3 times the diameter. And apart, these are the various modes of failure, and the most common way of failure for stone column that is observed in the site and at the in the laboratory model studies is the bulging method. For a single stone column, for end bearing and floating stone columns, the failure mechanisms have been shown, and this has been referred Indian Code 15284 Part 1. In figure A, we can see that the long stone column, that means length is greater than 3 times the diameter, and it is resting on a firm strata. The bulge is taking place, and the bulging has been shown with the help of the dotted lines, and the maximum formation is observed at a depth of 2 times the diameter when only stone column is loaded. It has to be observed here that in all the 3 cases that we are referring in this particular figure, only stone column loading is carried out. In second case, for short stone columns, the shear failure takes place. Whereas in case of floating stone column, where the stone column is not resting on an firm strata, the punching failure takes place as it doesn't have any end bearing. It simply penetrates into the soil. Now at the site, how to monitor as to what amount of aggregates, whether the densification that has been done has been accomplished or not. We may say that this is the density that should be achieved, but achieved. How to monitor that? So with the help of the technologies that are available, this is the monitor that is available to the operator of that particular machine. And once the stone column is completed, this chart, energy consumption chart, can be printed, and this will inform us as to whether the density that was expected has been achieved for the concerned stone column. If there is any issue regarding the density or any other parameter, then that particular stone column will have to be reinstalled. So this will help us, because we cannot go to a depth of 10 meter and ascertain whether the density is there, because during the compaction of an embankment, we can make use of a sand replacement method or a core cutter to find out the in situ density. But in situ density at a depth of 5 meter or 10 meter cannot be found out. So this technology, where the energy used or the energy consumed by the machine or the probe for installing that particular stone column, helps us in deciding whether the stone column that has been completed is in a good condition or not. Now the site visit that we had carried out in 2010 to at the Pipawa project. Pipawa is a port which is located near Bhavnagar in the Arabian Sea, and the contractors were Keller, so these are the details, the gantries, etc., that was there. At this site, both methods were adopted, and fortunate enough to have a look at both the methods at the site. Sorry, the probe, water jet coming out, and the inserted position of the probe at the site. In the case of a wet, in the dry, in case of the JCB can be seen as loading the hooper, and here the opening of the window that I was mentioning can be seen here clearly, is visible clearly. The hooper goes to this height and then it empties the entire consignment of aggregates into this particular window, and which falls into the hole below. This is a completed stone column by dry method. Now at site, once the stone column comes to the ground level, stone column installation is complete, then the diameter is ascertained. Now here we cannot find out as to what is the read. Made use of this particular the construction equipment Phavda. So everybody knows what is the normal size of a Phavda. So that is the diameter of this particular stone column here. So this is a dry stone column constructed with a dry method. Some details. Since we had 2 different methods adopted, so that means we'll be having 2 different values of N, that is SPT value N. So for the top soil, which was of Murum fill, the value of SPT N was 9, and beyond 2 meters to 12 meters, the thick marine clay was there, and the value of N was 4 to 6, and beyond the 12 meters, they had observed a weathered rock layer, and the value of N was greater than 50 blows. The geotechnical problem that was given by the client to the Keller was to improve the strength, limit the settlements, because that was a port and a lot of heavy container traffic will be using that particular area and the site entire. So pavements, etc., and the structures that were going to come up in the region or the area of Pipavav port. So they wanted the bearing capacity to be and minimization for the wherever the structures were going to come up. So the solution that was suggested by Keller was to have vibro stone column of diameter 900 mm with a triangular grid spacing of 2.5 meters center to center. And at few locations, these stone columns, though we have seen the depth of the hard strata was 12 meters, but in some cases, they had taken the stone columns to a depth up to 15 meters too. So total 1,44,000 linear meters of stone columns was done at the site. The duration for the project was 10 meters. 4 rigs were made use of, and the energy that was used for both the probes has been mentioned here: 55 kilowatt hours and 300 kilowatt hours. The execution details: the aggregate size for wet method was 70 to 35 mm. For dry method, the size of the aggregates was smaller. You all know, 35 to 12 mm. The loss of aggregates for the entire project was about 15%, and the diameter of the probe was 500 mm, and the length of connectors to go up to a depth of 10 meters and beyond was 5 meters. They had, as usual, the has to be. So this was the arrangement that is done at the site at Pipavav. So over the other, they were welded. Then the loading ram was provided, and the test was carried out. And the strength after ground improvement, they had recorded as 150 kilopascals. So with this, I conclude the presentation, and I hand over the forum to host Vivek.